Thank you for watching the presentation of risk-sensitive reward-free reinforcement learning with CVaR. This work has been accepted to ICML 2024. Today's presentation will include these 6 parts, which covers from the introduction, problem statement, the methodology we used there to solve the problem, the experiments, and a conclusion. We first introduce some background of reinforcement learning. In RL, the agent and environment interact at discrete time t, and at each time step t, the agent observes the state st, take action at, and get reward rt from the environment, and then go to the corresponding next state st plus 1. However, there are some limitations of existing exploration algorithms. The first thing is that simple exploration method, which can be inefficient for discovering high reward states, may result in high sample complexity. And these sophisticated exploration strategies that are efficient for pre-specified reward function exist. And the second one is that in practice, reward functions are typically iteratively engineered to encourage desired behavior. If these methods are applied for each time reward functions are updated, it can be sample inefficient. To solve these limitations, a framework called reward-free RL has been proposed. The goal of reward-free RL is to develop a more efficient exploration approach that does not rely on explicit reward function. And this framework includes 2 phases. The first one is called the exploration phase, in which the agent efficiently explores the environment without reward information through protocol 1. And the second phase is called planning, where the agent derives a near optimal policy with any given reward function, only using the dataset gathered during the exploration phase and without further interaction with the environment. In this work, we also consider the scenario of risk-sensitive. In safety-critical scenarios, decision makers prioritize mitigating low probability but high-impact risks. Many risk measures have been investigated, but coherent risk measures are preferred due to their properties. These 4 properties make coherent risk measures capable to capture regional risks and also presents the risk preference of the decision makers. In this work, we using conditional value at risk, which is defined in this way. And one important fact is that CVaR is coherent and it can effectively quantify the average outcome in the worst tau percentage of scenario. So the motivation of this work is that is it possible to design provably efficient risk-sensitive reward-free RL algorithms? So our methodology is to adopt the reward-free RL framework to design an efficient CVaR reward-free exploration algorithms, and also using the planning phase to derive a PAC algorithm to solve CVaR with any given reward function based on the dataset. So you may ask, what is PCA? So a PCA is defined as this way, which means the mean of the error between the optimal CVaR value with the estimated CVaR value is less than or equal to epsilon with probability at least 1 minus delta, which means estimation is really good. And compared to traditional Markovian decision process, we adopt the idea of augmented MDP. In augmented MDP, the existence of an optimal policy that is deterministic and Markovian for CVaR has been established. And the augmented state space is denoted in this way, where 0 to h, the range 0 to h is augmented space for initial budget B. The B comes from the definition of CVaR. We follow the idea of dynamic programming. We define the value functions in this way and also reformulate the objective by replacing the inside part to be the value function V And the goal is actually becomes to optimize the CVaR value and find the corresponding optimal policy rho star with optimal initial budget B1 star. Because the Bellman equations in risk neutral case is not applicable anymore, we defined the Bellman equations for CVaRL. And similarly, we define the optimal conditions in as follows. And one thing you need to notice is that the initial budget is updated based on the reward. So you may not see the reward directly from the equations of V and Q, but actually the reward function is affect the update of B, which further change the value of impact the value of V and Q. One thing we need to notice is that the optimality has been demonstrated in this work. Now we are going to introduce our methodology here. Before we present our CVaR exploration algorithm, we first provide a key lemma. The lemma says that an algorithm is epsilon delta PAC for CVaR exploration with a given risk tolerance tau if for any reward function R and for any B1 in 0 to H, the error between the value function under the true transition probability and the value function under the empirical transition probability is less than or equal to epsilon tau divided by 3. This lemma establishes a connection between CVaR IFRL with risk-neutral reward-free RL and solves the complexity added by the adoption of CVaR. So firstly, we assume the optimization error in planning phase is bounded. This could be easily satisfied by existing CVaR algorithms, and we also propose such a planning algorithm in our planning phase, which will be mentioned later. The idea here is to define an estimation error, which is actually the difference between the estimated Q value and the true Q value. And we want to find an upper bound for this error. We first define upper confidence bound in this way, which is recursively defined as follows. When H equals to H plus 1, the error equals to 0, but at the other time, the upper error bound is defined as a minimized over this. And this also refers to equation 8 in algorithm. And notice that the beta here is a threshold function, is actually an input to the algorithm, the choice of which will be discussed later. And here we also consider an event in which the difference between the estimated transition probability P and the true P is measured by KL divergence, and the KL divergence is less than or equal to this parameter. And we have shown that for any policy rho, any reward function, and any B, the upper bound we defined before is actually the true confidence upper bound for the error. And this will always hold on this event. Now we are able to design our algorithms. For the sampling rule, we define the exploration policy pi t plus 1 is a greedy policy with respect to the upper error bound. And for the stopping rule, the algorithm will stop at the time when the error upper bound is less than or equal to epsilon tau divided by 3. And this is an overview of our exploration algorithm. Because we have established the theorem that the error upper bound is independent of the reward R and the initial budget B. So in the exploration phase, we can really perform like reward free, but also control the upper bound and also control the upper bound of the error is bounded. And here we present some theoretical guarantees of our exploration algorithm. So the first thing that is that using this kind of threshold, the CVaR IF UCRL is PAC for CVaR IF exploration, and the number of trajectory collected in the exploration phase is upper bounded by this value. And compared with risk-neutral reward-free approaches, the denominator of the bound we obtain is related to the risk tolerance parameter tau. This is expected since CVaR is interpreted as the mean of the tail distribution with an area on the curve equal to tau, and it will require more trajectories for smaller tau values and few trajectories for larger tau values. And now we are going to introduce the planning algorithm. So the framework consists of the following steps. So firstly, we compute the empirical transition matrix based on the dataset collected by CVaR IFUCRL. And then we find a near optimal policy by employing an approximate CVaR solver, which can be any algorithm designed to find an suboptimal policy for CVaR with non-transition matrix and the reward. And algorithm 2 here provide an overview of the CVaR IF planning framework. Now we introduce more about the approximate CVaR solver. We can know that actually iteratively solves the Bellman optimality equations in a dynamic programming manner. The gradient policy induced by the resulting Q star actually yields the optimal policy without errors. However, we notice that the initial budget of B is continuous, which means our CVaR VI algorithm actually faces computational challenges. And the maximization problem is actually of a non-concave function, which is quite challenging. So to solve this challenge, we use a discretization method, which is presented in algorithm 4. So we discretize the reward function by set the R to be on the eta grid. And since B is updated based on R, actually the B can be further discretized in this way, where B hat equals to n times eta and n equals to 0, 1. So which means B hat always stand in the eta grid. And we also analyze the computational complexity and the error of our discretized version of CVaR VI. So the first thing we have demonstrated that is this algorithm has a runtime of big O of S squared times A times H times eta minus 2. And by setting the eta equals to this value, so actually the runtime is of big O of square S squared times A times H third divided by epsilon square and tau square. And furthermore, we notice that if we choose an eta less than or equal to this value, we can ensure that the optimization error is actually less than or equal to epsilon divided by 3, which satisfies the assumptions, which satisfies the assumption we proposed at the very beginning of the exploration phase. One thing we want to emphasize about our approach is that the adaptability of our algorithm. We can know that actually for any tau prime larger than tau, the exploration data set we obtain contains the requisite information for conducting CVaR IFRL with any higher risk tolerance tau prime. This underscores the adaptability of our exploration process to different levels of risk tolerance for tau. And we also analyze the lower bound for any CVaR IF exploration algorithms. And we can see that the trajectory is lower bounded by big omega of S squared times A times H squared divided by tau times epsilon squared. Compared with the lower bound, the upper bound established before has an additional factor of H squared and 1 over tau, while being tight with respect to the parameters S, A, and epsilon. And if tau is a constant, our result is nearly minimax optimal with an additional factor of H squared. We also validate our algorithm in experiment. The environment we use here is a grid world consisting of 21 times 21 states, where each state offers 4 possible actions. The agent can go up, go down, go left, or go right. And consider the randomness. The agent will move to the correct state with a probability of 0.95 and to one of the other 3 directions with a equal probability. And we also consider 2 different reward setup. So the first reward setup is that the agent start at position 1010 and the reward is 0 for most states except the destination 1616 where the reward is 1. And the second reward setup we use is that the reward is 0.5 for most states except at the destination where it is 1. And we mark a 0 reward zone as X from 1210 to 1216, which can be regarded as obstacles. And this is the result of running our CVaR via DISC over these two reward setup. We can see that actually our output policy performs very similar as the optimal policy. And the arrow is bounded by epsilon times tau divided by 3 for both cases. So in this work, we have introduced CVaR-IF, which is able to solve CVaR-IF for any given reward function after a singular reward-free exploration. We also propose an exploration algorithm and establish the upper and lower bounds for the sample complexity. We developed a planning algorithm equipped with CVaR-VI and discretization version to generate near optimal Markov policies based on the exploration dataset. And we also demonstrate the adaptability of our exploration algorithms to different levels of risk tolerance. And we also derive the lower bound for any exploration algorithm in the CVaR reward-free framework. We have also validated the effectiveness and the practicality of our CVaR-IF framework. And these are the reference we mentioned in these slides. So that's all for today's presentation. We really appreciate your time to watch this video, and any comments and discussions are welcomed. Thank you so much.